Welcome guys. So welcome to my real analysis video. So this is a previous real analysis topic, and today I want to talk about some interesting topic. Basically, it's famous results. There's no Lebesgue major in the infinite dimensional space. This is people somehow like to say, but seldom people write everything and make video. So I just make a video. So the famous results. There is no, so basically there is no infinite dimensional Lebesgue major. Okay, basically unless trivial. Okay, so let me explain what's going on. So usually we require a major to have three properties. So for example, let's consider the Lebesgue major. Let's say lambda n on the Euclidean space Rn. Have the following three. So you can check out my previous video, which is describe how to construct the Lebesgue major. But I think these three of them are very trivial, okay, and very intuitive. The first one is that for every x belongs to n dimension, there exists the open neighborhood. So this is NBHD, open neighborhood of x, such that the measure of this nx is finite. Okay, so this is almost trivial, right? Because in the n-dimensional, you can pick up n-dimensional ball, or n-dimensional, infinite dimensional, you can make a cube, and then you know that the Lebesgue major of the cube must be finite if you, let's say you choose that is to be 1, okay? And second is that for any x or any a which is open and non-empty, and the Lebesgue major of the a must be greater than 0. Okay, so this one is almost very important, right? For example, if your major, let's say on open ball is 0, or the open cube is 0, then somehow every open set should have the major 0. So this property is also very intuitive. The third is that the translational symmetry. So translational invariant. So this is also a common property of the Lebesgue major, or basically any major you think, right? So for example, you have a box with the area 1. If you shift is by any length h, then this should be area 1. So let's say I define a thx to be x plus h in a n-dimensional, which means that th for any set a, take the Lebesgue major, I use lambda n, will have the same area, same volume for every h. Okay, and so now this is common property. So theorem for the infinite dimensional banana space. Basically, you need to add a condition called separable. Okay, so this is a very technical condition. Basically, I'm not explaining here. You can imagine that what I'm talking space is like like L2 space or R infinity, that kind of space. But basically, separable you can view it basically has a basis which is countable. So you can, one simple idea is that there's a countable basis. Okay, then there's no such measure. Okay, so basically the 1 and 2 and 3 cannot both these three conditions cannot both be satisfied. So can both satisfy. Okay. So proof look like this. Okay, so let's quickly give it a proof. Okay, so proof is not very difficult. So imagine that let's consider let's say right, so it's separable, right? So you can imagine that your space, since it's infinite dimensional, so you can imagine that locally you can choose an infinite dimensional basis, countable basis. Right, so for example, that you can choose, that E1, E2 is to be your orthonormal basis locally. Okay, so yeah, for example, you can if you take the R infinity or L2 space, then you basically obvious these are the common L2 space, let's say L2Z. Or if you're working on L2R, you can choose the Hermite polynomial or the wavelet or the Fourier coefficient or trigonometric function. But however, you just take all the also normal basic basis. And notice that okay, so let's say let's say you pick some 0, 0. Right? So this is the origin, which is a infinite dimensional origin. But who cares? You just pick some point, and then there exists let's say there exists a ball, right? Because by the first condition there is a neighborhood, so there is a ball with the radius delta, which let's say delta such that this lambda, right? That's this measure on this delta is less than infinity, right, by the first one. So lambda now that's proved by contradiction. Suppose lambda is some measure which have the 1, 2, 3 properties. Okay, and since I have locally, right? So let's say I have this, let's say pick an origin and I pick a ball with radius delta. Okay, so okay, so without loss of generosity, right? Without loss of generosity, I can choose this delta to be 1. Okay. Because if delta is not 1, I can just shrink. So let's assume delta is 1. So notice and in these local coordinates, right? You have the distance with EI minus EJ, which is the square root of 2, right? For any IJ. And not the same as J, right? So basically now you can count. Okay, so now let's choose this B. Let's say we choose some ball with radius. I think it's the coordinate, let's say EI divided by 2. So this is center. I think this is okay. And choosing a radius 1/4. Okay. So maybe it looks very stupid, but let's draw a picture. As I say, consider 2-dimensional. And then you have a radius 1, right? So this is your B0, 1. And I choose, so this I draw a small ball which has this, and the radius is 1/4. So this radius 1/4, and then you can put another which radius is here. That means 1/4. Okay. So you see the distance of this EI and EJ are basically square root of 2. Right? And the radius is basically 1/4. 1/4. But you can choose 1/2, but it's the same. Right? So you can see that these two balls will not intersect, right? Okay. But in the infinite, so R2 you can at least choose 2 balls, right? I mean, at least you can choose 4 of them, right? But let's say in infinite dimensional, right? So you can choose infinite balls, right? So there exists so you can choose infinite balls such that their radius they're at the center of EI divided by 2 and 1/3. Okay, so by the subactivity, right? But this guy is a subset of this small ball is a subset of all the open ball. So this guy should be finite, right? Because this is open. So by 2, this lambda of B EI divided by 2, 1 divided by 4 should be finite. Okay, but then also by third. By third is what? By third is that this guy, every ball has the same volume. Okay, so you have infinite balls. And each of them has finite volume. So then, which do not make sense, right? Because your B of 0 delta can eat all the BEI divided by 2, but let's say 1/4. So this is 1. And then where I from, let's say EI, I from 1 to infinity, and then you take major, right? So, and these are all do not overlap. So this lambda of BEI divided by 2, 1/4, I from 1 to infinity will actually become infinity because every of them, they have the same by the third property, the translational symmetry. Contradiction, right? Because this guy is finite. Okay, so equals to this, but by my assumption, by 1, this guy is finite. Okay. So we prove that if the major exists, then must be everything becomes zero, right? But if everything becomes zero, then violate this the second property. So this is the simple reason that why the back measure cannot sit in the infinity space. The one simple reason is just say that the infinite dimensional ball. So let me just tell you a simple reason. So simple reason is that the infinite dimensional ball can fit infinite smaller balls. Then there is a contradiction. Okay, so you can see that there's almost no way to mod out this fact. Okay, so this is the simple video that I make a small video to explain why there's no infinite, there's no Lebesgue measure in the infinite dimensional Lebesgue measure. So basically, if you study quantum mechanics, you want to define so-called path integral from 2 points, which is you work all the paths from A to B well into some countable in space, and which if you working like a Lie group or whatever, always infinity. Okay, see you guys next videos.